All right, so we'll take a look at one more example now of graphing and curve sketching using that process that's been outlined. We've done a polynomial, we've done a function that actually had two non-differentiable points in it, and then now we're going to take a look at a rational function. So the process is really no different. We'll start with the domain. The domain of this now is negative infinity to 1, union 1, to positive infinity. So now we're dealing with something that has a discontinuity at x equals 1. In this case, we know it's going to be the vertical asymptote. So that takes us into step 2. We know it's a vertical asymptote, right? At x equals 1. So the limits around a vertical asymptote, we would need to study the limit as x approaches 1 from the right, as well as the limit as x approaches 1 from the left. Each vertical asymptote will have two limits associated with it. It'll have approaching from the right and approaching from the left. So we would need then to go off to the side and compute these limits, which you've done before, right? This is straight out of chapter 2 stuff. This limit, actually, they both end up being positive infinity in this case. So, and again, that kind of makes sense. I mean, if you look at it, that's always positive, that's always positive. So use that as your guide to know what's about to happen here without having to overwork yourself. So we've got two limits for every vertical asymptote. We also still need the limits now of the end behavior. So for the end behavior, we would need the limit as x approaches positive infinity and the limit as x approaches negative infinity. And so when we compute these limits, again, this is straight out of chapter 2. I believe it was one of the later sections where we talked about limits at infinity. Both of these end up equaling 3. Put together, this tells us we have a horizontal asymptote at y equals 3. Right? If the end behavior approaches a finite number, then that's going to be where it limits, and that's going to be where your horizontal asymptote is. So in this particular problem, we had a few more limits we had to worry about and some different information coming from our end behavior. Now, in algebra, I normally have my students do a cross check because we know the graph may cross a horizontal asymptote. So to do the crossing check, that's where you actually take the asymptote, set it equal to the function, and you're searching for essentially a point of intersection. So if you choose to do the crossing check, this would be a good time to do it. This is, again, where you take the asymptote and set it equal to the function. If you do this, you actually find out it crosses at 0, 3. Now, if you don't do the crossing check, you'll absolutely figure it out with all the other information that you have. But because it's generally pretty easy to do, I'm a big fan of doing it most of the time. Okay? All right, so then step 3 would be our first derivative test. The simplified first derivative would be this thing here. We would take it, we'd set it equal to 0, and we could see very quickly we'd get a critical value of x equals negative 1. Now, that's great, but we also need to remember from the domain, x equals 1 is a horizontal asymptote, which is a discontinuity in the graph, which means we have to be on alert to what's happening around it. So I'm going to include the x equals 1 in my critical value list. So putting the number line together, a negative 1 and a 1. When you run your numbers, you get a negative, a positive, and a negative. And just to be clear, maybe I should have mentioned it before. I know I mentioned it in a video a while back, but feel free to mark VA on that just to remind yourself what it is and not make the mistake of including it unnecessarily. Okay, so let's see here. We've got an interval of decrease from negative infinity to negative 1, union 1 to positive infinity. We've got an interval of increase from negative 1 to 1. And it looks like we have a relative minimum only at negative 1, f of negative 1. That's where, hopefully by labeling it, you would have caught that this is not a maximum, right? We're not changing from increase to decrease at 1 because 1's not actually on your graph. So by marking that, we caught it, and hopefully we weren't going to include it as a relative maximum, okay? Good. So moving on to step 4, the second derivative test. This is where we take the second derivative, and here is your simplified second derivative. We'd set it equal to 0, and again, pretty quickly you could solve this and see that you'd get x equals -2 as a critical value. But just like the last one, we have to make sure to include this +1 in there as well, since it's not actually on our graph and it could affect intervals of concavity. So I'll take my second derivative number line, and I'll put my -2 and 1 on there. When I run those numbers, and let me mark this again just to be consistent. When I run those numbers, I get a negative, a positive, and a positive. So we are concave down from -infinity to -2, and then concave up from -2 to 1. Then we have to stop, right? Even though there's 2 pluses on either side, 1 is not on the graph. Union 1 to +infinity. That also tells us we have an inflection point at -2, f of -2. And now for the intercepts, step 5. For these intercepts, I found -1, 0, and 0, 3. So again, when you actually went ahead and found the intercepts, that's where you would have also caught this. But again, this is a nice step to include. It's not very difficult, and it sometimes gives you some good information. Okay, so I think we're ready to put this graph together. All right, so the information that I'm looking at, the information that I'm definitely going to start with is the domain, the vertical asymptote. So for the vertical asymptote, I'm going to sketch that in here at x equals 1. My horizontal asymptote right here is going to be at y equals 3. I also have this behavior around the asymptote, this stuff up here, and then I'm going to come down. I'm going to focus primarily to start on intervals of increase and decrease, as well as these intercepts. And then once I get something on my paper, I'll circle back, make sure all of the other information matches. All right, so in terms of intercepts, the 0, 3 would be right there. The -1, 0 would be right here. Okay, so it looks like we would start out decreasing until -1, increasing up until 1, and then decreasing from 1 on. So this is kind of what I'm seeing. We would be decreasing to -1 and then increasing up all the way, looks like to infinity, on the left side of that asymptote. And then we would be decreasing to the right side of that asymptote over here. Putting the arrows on the ends, and always mark that in behavior. And so let's see if it all works. I would be decreasing from -infinity to -1, increasing from -1 to 1, and then decreasing again from 1 to infinity. I've got my concavity here where I'm concave down from -infinity to -2. So this would be about -2. There's that inflection point where I'm concave down there, I'm concave up there, and then I'm concave up all the way to the asymptote, and then continuing to be concave up from 1 to infinity. So it looks like everything works out with all of our information. Again, it's a lot of information. Just get a graph on your paper and start tweaking it along the way. If you got to go back and readjust some intervals in terms of notation, that's sometimes something to remember as well. But for all of these types of problems, the hidden parts, the asymptotes, the non-differentiable point, things like that, those are the easiest ones to overlook. So if you're getting some conflicting information or some things that are contradicting each other, it's probably hidden in there. So just go back and review that stuff. Hopefully the process has been laid out in a way that it's relatively easy to follow and understand. And this is a big component of calculus, is this analyzing graphs. And so put in the time, and I think it'll go well for you.